Very good afternoon to all. Today we are going to discuss about the theory of computation. So theory of computation is a fundamental course for all the computer science students. Even it is useful for the non-core students of the CSC, that is useful for the mathematical students also. So we will discuss about the step-by-step process of the theory of computation. Here computation means step-by-step solution for any real-world problems. So like for example, so if we have any greedy approach or any dynamic problem solving, so we will give with the help of the theory of computation, we will give all the type of the solutions. So here, so coming to the fundamental of theory of computation, so the main thing is it is a branch of computer science that deals with the any real world problems, so that we will solve efficiently, so by using of this theory of computation. So coming here, the main example of these theory of computations are, so finite automata, this theory of computation we will also call it as formal language and automata theory. Formal language and automata theory. In the name itself we have formal language, so we will develop this automata by help of the formal languages. So what is mean by automata first? So automata develops formal mathematical models, so that will give any computational problem, that give solutions to any computational problems in the real world. So coming to the formal language, before going to discuss about the formal language, we will know with the some terms like a grammar. So we all know that grammar that contains some alphabets, strings. So what is mean by alphabet? Alphabet, that means like A, B, C, and so on. So even we will have some digits like 0 to up to 9. So coming to the string, the collection of these alphabets we are calling it as the string. Sometimes it will help us, we have some null strings like epsilon. So not only the alphabets and strings, we have the collection of strings that we have some grammars. Maybe we have the different type of the grammars that we will see in the later sessions. So coming to the grammars, we have, in this we have non-terminals, terminals, production rules, and symbols. Non-terminals that will generate some strings by helping of some terminals, by helping of replacing some terminals. And we have some production rules that contains non-terminals and the terminals. So for suppose non-terminals that we have at the LHS side, and at the RHS side we have some non-terminals as well as the terminals. So this form we are calling it as some production rule. And we have some start symbol. So start symbol means where we are start from the automation, that we are calling it as the start symbol. So this is the main thing of the grammar. Contains the 4 tuples, non-terminals, terminals, production rules, and the start symbol. So coming to the finite automata. So coming to the finite automata, we have the different types of the finite automatas, like deterministic finite automata and non-deterministic finite automata. This non-deterministic finite automata and deterministic finite automata that comes under the finite automata without output. without output. So even the finite automata that contains with output. So with output we will discuss like Mealy machine and the Moore machine. All these finite automata rules that we will discuss with the help of the Noam Chomsky rules. So here the Noam Chomsky, they have identified the rules in 1960s. So based on these Noam Chomsky rules, the finite automata that defines the grammars and all the grammars that defines all the rules of these finite automatas. So we will discuss about the finite automata rules on the Noam Chomsky grammar. Noam Chomsky grammar. So here we have the types. Next. Type. Language. Grammar. And production rules. So for the type, the grammars we have like type 0, type 1, type 2, type 3. So coming to the type 0, the language we are calling it as the recursively language. Recursive language. So the grammar we use here is the Turing machines. So we also call it as the automata grammar. Automata. So for the type 1, we will use the context sensitive language. Sensitive language. So that we will call it as the linear bounded automata. Linear bounded automata. So next one we have type 2, that we have context free language. Simply we will call it as the CFL. So for this the grammar we will use is context free grammar. So next last one we have the regular language. So the grammar we use is regular grammar. So all these are the Chomsky rules. Coming to the production rules, the Turing machine, that we have no restrictions for the production rules. These are the very, very important of the production rules. No restrictions whenever we are writing the Turing machine, that is the type 0. So coming to the type 1, so we have alpha, A, beta. So that derives, so alpha, gamma, beta. So that is the basic production rule. Coming to the type 2, that is the context free grammar, that we have the production rule is A derives gamma. Coming to the type 3 regular language, we have A derives alpha A, B, or A derives alpha. So if we discuss about these linear bounded automata, so alpha and beta may be the terminals or the non-terminals, any type. So A, that is only the non-terminal. That means coming to the type 1 language, at least a single non-terminal is sufficient for the LHS side. Coming to the RHS side, so maybe the terminals or the non-terminals that we can use. Next is the type 2 context free language. So only the single non-terminal at the LHS side. Gamma, this is the terminal. So there is only the terminal or the non-terminal at the RHS side. So coming to the type 3, so at the LHS side we have only the non-terminal. So at the RHS side we have the terminal as well as the non-terminals.